Hello, here we are today to learn about PCM, that is PCM modulation, demodulation, and compending also. So what is PCM? Is pulse code modulation, that is per sample value it is being converted to a code, that is analog signal is converted into digital data by using pulse code modulation. So what are the basic blocks of pulse code modulation use? The first block is a sampler, the second is a quantizer, the third block is nothing but encoder, and then it is a parallel to serial converter. So now the sampler is simply a multiplying of pulse sampling wave and the analog signal, or we'll call it as a pulse wave and analog signal. Quantization is approximation of the signal, and then it is encoding, that is converting the analog value into digital data, and then it is parallel to serial converter. So what you have is the ADC IC, that is 0809. This is the 0809 IC, which is itself is a sampler, quantizer and encoder enclosed in this particular IC. After this IC, what you have is a latch which has been used, as it is a 173 IC, and then it is nothing but a parallel to serial converter, that is 151 IC, which has been used by, right? Now what is the input to this particular that is ADC is analog input. So what you have is two analog generators which are provided on this particular kit. One is the a fixed sine wave, and the other is a variable, that is you can change the frequency as well as amplitude. For our experimental setup, we are going to use the fixed sine wave. Now once you have the fixed sine wave, I am going to show how is the fixed sine wave. So we'll see, first observe the fixed sine wave. So I have connected the fixed sine wave now. So we'll see the CRO on CRO, the fixed sine wave. So we'll say the auto set. Once we do the auto set, here you can observe is this as the fixed sine wave. So your fixed sine wave frequency and amplitude you can measure later, and you can have the notification of the same. So it's a 1 kilohertz sine wave which has been represented with peak to peak value, that is 1.6 volt, right? Now this will be applied as an input to the input point of the ADC. So where is the input? Here, this is the input of ADC. Now this is the sampled output, it is quantized. You have latched, that is going to say store the data for a particular time period, and that time period is nothing but that is equal to OE bar, and then it is parallel to serial converter, and here you have the serial PCM outputs corresponding to per sample value. So what are we going to observe now? How this PCM output is going to be generated. So I am taking a second probe of the DSO, and one by one we will be observing the waveforms. So what we have is SC, that is what you call it as a start of conversion. So we'll be first observing the start of conversion, where exactly the point where the conversion starts with. So once again we'll go for the waveform, that is start of conversion. So it's a point, as I said, that it will start with conversion for each sample value. So you can say that there are 8 samples which are been present. How 8 samples? As I go to measure and I press the frequency for the channel 2, what you can see is the channel 2 frequency is 7.8, that is approximately 8 kilohertz, and our analog signal is 1 kilohertz. So what you can say is in one cycle of, or say 1 kilohertz cycle, there are 8 samples which are been there. 4 samples at the positive half and 4 samples at the negative half. How do I measure the samples is, see here, once you start from this particular sampling instant, that is rising edge of each sample to rising edge of the next sample is one sampling instant, that is we call it as one sample. So there are going to be 4 sampling instants in the half, that is a positive half, and 4 sampling instants in the negative half, right? Now what I'll do is I'll remove the analog signal, and we'll see now the synchronized waveforms for SC, EOC. What is EOC? EOC is end of conversion. So what I'll do is I'll just connect SC to the second channel, that is EOC, and the first channel I'll be applying, that is we'll be observing what we can see is the SC waveform. So I have connected now SC and EOC together. We have already applied the input analog signal to this. Now we can see both the signals together, that is SC and EOC. What we can see is the SC and EOC, you can see there is some difference between the two. So wherever there is SC, The EOC starts after the SC. Now what we can say is the start of conversion and the end of conversion. So the rising age of SC and the rising age of EOC, what lies is the conversion time period, correct? So it's going to be the conversion which is going to take place between whom? That is the rising age of SC and the rising age of EOC, which is going to be there. So this, if you measure, you have to measure the time difference between these two. So you can measure it by using on the DSO, you measure it by using measure and cursor option. Place the cursor at the particular, that is the points, and what you can see is the amplitudes, the difference between the time durations, which you can say. One cursor over here, the second cursor will be placing it at the rising age of the EOC. So what you can see is there is a delta difference, and that delta difference is of 84 microseconds which has been there. You can see. So this is what you call it as the conversion time period, which we represent by tau c. So this is start of conversion and what you can say is end of conversion, right? Now what we'll see is EOC and what we'll look for is, we'll see the PCM output first, and then I'll show the synchronized waveform with respect to that is the other OE bar or clock and so on. So what I'll observe now is nothing but the PCM output. So here we have I am showing the PCM output. So once again we'll just auto set. Now see, channel 2 is the PCM output which is seen. What you can see is at the channel 2 is there are random bits which are being represented over here. What are these random bits? So these are the random bits and they are active low. The PCM output is nothing but active low. Now why active low? Because the latch is enabled and it is active low duration during which the PCM output will be existing. So it is still OE bar is active low, your PCM output is going to be existing. So we'll say, see here, now what I have done is I have connected OE bar of the latch and have connected PCM output together. What you can see is it is active low. Who is active low? OE bar is going active low and the PCM output will be held till OE bar is active low. So you can see the synchronization between the OE bar and the PCM output which is going to be seen over here, right? Now this is OE bar. Now what we'll see is the PCM output is being controlled or parallel to serially it is being controlled by a 4040 clock. So the clock 8 cycles will be synchronized with 8 bits of the PCM output. Now what I'll show is, I'll show you the 4040 clock and the PCM output together on the DSO. So what you can see over here is, see, the PCM output synchronized with 8-bit clock pulses. So here, this is the 4040 8 clock pulses which are being existing, and these are the 8 bits which are being converted by the PCM encoder to some bits which has been there. So this is 4040 and the PCM output. So you can see synchronization, that is the clock controls the PCM output parallel to serial curve. First clock, first bit, second clock, second bit, third clock, third bit. So in sense 8 bits are there, all 8 bits will be transmitted at the output end, right? Now what will be next saying is, now you have the reset, that is your clock will be reset after the 8th clock pulse. So what I am saying is, now 4040 clock pulses with what you can say is the reset which has been there. Once again auto set. What you can see is the 4040 clock is reset after the 8th clock pulse, means the falling edge of the 8th clock pulse and the rising edge of the RST, that is reset, is synchronized with each other. So your clock is reset after the 8th clock pulse of the, that is your clock itself. So this is PCM output, 4040 clock, the RST of 4040, and so on. So this is your PCM output. Now coming to the decoder side, what is at the decoder side? You have once again a serial to parallel converter which is over here. Then it is the it is the latch which has been holding over here, and instead of ADC, now it is going to be the DAC, that is R2R ladder type of a DAC which has been used. This R2R ladder DAC output is passed through the low pass filter, and what you get is the LPF output back again, right? So these are the synchronized waveforms or synchronization or PCM output which has been shown. I'll be just, as I said, these are the reference waveform which I have drawn for you. Analog signal, the 8 clock pulses of start of conversion, the EOC which is going to be after the SC, then it is OE bar, latch enable bar, or we call it as output enable bar. Then this is the PCM output. This is the what you call it as the 4040 clock pulses. Then it is reset of 4040 clock. Then this is the DAC. How the DAC is, for every sample value the DAC gets changed, that is digital value will be converted back to again analog signal. So you can see a step size waveform for the DAC which is seen, and then the DAC is passed through the low pass filter, and this is your original signal back again. That is, the DAC follows the LPF. What you can say is the DAC is nothing but, or we can say the LPF is nothing but same as the DAC. So this is your LPF output which has been produced, right? So this is regarding PCM. Now we'll come to compended PCM. Now instead of saying compended PCM, what I'll show is nothing but the compended that is A log compending. In this I'll show you the A compending part which we are going to observe for. Here now what I'm using is nothing but a variable, that is a generator, and what will be applying is this variable generator will be applied as an input to the A compender. Now what is compending is, during the quantization there is an error which has been existing in the, that is a PCM. So what happens is the signal to noise ratio of PCM system is nothing but goes low. To increase the signal to quantization noise ratio of PCM, we go for the compending process, where the signal is compressed at the, that is a transmitter end, and it is expanded at the receiver end. What does that mean is, this means that the weak signal is nothing but amplified and a strong signal is nothing but attenuated. So what you have is the process, that is A compending and mu compending. These region wise the process, that is the compending, A compending or mu compending are used. Here we'll see the compending process. Now what is done is, A compender output, the analog signal is applied as an input to the A compender, correct? Now what I'll do is, we'll connect the CRO probe to the A compender output input and the second channel to the A compender output, right? Now we'll observe the waveform again on the DSO. Let us check the waveform. See, this is the original signal, this is the compended output, correct? So there is a compending, there is a logarithmic amplifiers which are being used so that they are attenuated, and amplifiers to amplify the weak signals. Now as you change the amplitude, so here it's a change in frequency. If you change the amplitude of the signal, the compended signal amplitude is also changing. Now what you need to do is, with variation in the amplitude of the signal, you need to observe what we call it as the different waveforms. So change the amplitude to 0.5, change the amplitude to 1.5, change the amplitude to 2, 2.5, 6, 3, 3.5 and so on, and observe the compended output, and then draw a graph which is going to be input to the compender versus output of the compressor, input to the compressor and output of compressor. Now as a ready, you can see the characteristics also can be observed on the DSO with the XY mode. So on the DSO, how do you observe the XY mode is, go to the display option of the DSO, you go to the one second, go to the right display option of the DSO. In the display option of the DSO, this is the display option of the DSO. So once you press the display option of the DSO, what you will get is a format, right? In that format, use the XY mode of that particular format. Now what you can see is, yes, the compended output, it is the expansion of the, so if you observe the optimum, that is optimum we'll say waveform, or we'll say characteristics of a compender, you can see that this is the shape of the compended output, correct? So this is your compended signal. Now the same signal will be expanded. So what I need to do is, I need to now apply the compended output, correct? I need to apply the compended output as an input to the expander. So what I'll do is, compressed output, apply it as an input to the expander, and will observe the expander output and the expander input together on the DSO. So what I have is input of the expander, output of the expander together on the DSO. So once again, this is input to the expander and output of the expander. Now once again, I'll put the CRO in the XY mode. So you can see that is display option, one is the display option, and put the CRO into the XY mode. What you can see is, yes, the characteristics which has been observed is, this is the characteristics. Just once again, we'll just go through the waveform. 1 minute. I'll just change the amplitude of the signal so that a better compended output can be, right? So here you can go for a better output now. Now we'll put the CRO in the XY mode. Display, sorry, auto set. Then go to display and then press 1 minute. Display and XY mode, correct. So this is the expander, that is the characteristics. Similarly, as you have taken the compended, that is readings, you also take the expander reading, and you can plot the characteristics by taking the reading on a simple graph paper. So this is all about PCM. Now if you want to perform PCM in presence of compending is, instead of directly applying the analog signal as an input to the PCM, you have to first give it as an input to the compressor. Output of the compressor will now go as an input to the expander. Other procedure is same. Now the DAC output, instead of directly passing it through the low pass filter, you have to apply it as an input to the expander, and then output of expander pass it through the low pass filter, and that low pass filter output is going to be their original signal back again. So this is the process for whom? That is compended PCM, correct? This is the real time, that is the we'll say technique which is used to improve the signal to quantization noise ratio. Thank you.